Well, hello, ladies and gentlemen. Let's continue on with our treatment of the first law of thermodynamics for a closed system. So today's topic will continue on and do another example. We did plenty of examples last time, so maybe we'll keep the lecture a little bit short today. We'll do one example involving a two-phase system with H2O as the fluid. We'll be heating up a gas liquid mixture, saturated mixture, and determining how much time it takes to heat up a mixture of vapor and liquid using an electric heating element. That'll be the plan for today. But so we'll do this example, and then we're going to move on to what's called the du-dh property relationship. We're going to revisit specific heats. Remember CV and CP that we defined earlier about a week ago, back in chapter 3? Well, we're going to use specific heats and get the full power available with the concept of specific heat and use it to derive equations that allow us to calculate the change in internal energy and the change in enthalpy for a system using specific heat. So we're going to derive some relationships that allow us to calculate the change in internal energy and enthalpy of a system using specific heats. Pretty neat stuff. So let's proceed here for our example. We have excuse me, we have initially a two-phase system composed of 25% quality, 25%. So this is H2O with a quality of 25%. So basically by mass, we got saturated vapor and saturated liquid in a container. Liquid vapor in a container. Now this is a rigid container. It's a rigid container, and inside of it is a heating element or a resistor through which current passes. So we have a little heating element here. There's a voltage difference across the wires, delta voltage, and then there's a current passing through the wires. So we got electric work or electric power being done on the H2O in this rigid container. So let's go over the details a bit more here. There's 5 kilograms of H2O inside the container. The initial pressure is 100 kPa, so approximately 1 atmosphere. As I said previously, the quality at state 1, the initial quality of the H2O is 25% vapor by mass. And then, of course, we have the heating element. A current of 8 amps flows through the heating element, and the voltage difference across the wires is 110 volts. So basically, household mains voltage. So, this rigid container initially contains a mixture of H2O, liquid and vapor. The heating element is turned on. We dissipate energy. We heat up the H2O until all of it becomes a saturated vapor. So state 2 is a saturated vapor. So quality at state 2 is equal to 1, all right? So what are we supposed to find? Let's find out how long, delta T, how long it takes to boil away all the liquid and to get a saturated vapor in our rigid container. Okay, so this is a bit different problem than what we've been used to before. Previous problems used either an ideal gas. So we're able to use the ideal gas law and to use ideal gas property tables. This problem involves H2O and it involves a two-phase mixture. So we're going to have to use saturation tables to calculate change in internal energy and such. It also has time in here, delta T. We're not calculating a heat transfer rate or a total heat transfer or a work or something. We're calculating time required to boil away the liquid H2O. Okay, liquid H2O, and get saturated vapor. So let's get started here. We'll write down our assumptions as we go along. So that's why I have the assumptions section on the next board. We'll write the assumptions down as we go along. Okay, so let's begin the analysis here. So we're looking for a time required to undergo some process from state 1 to state 2. If you like, let me put up a TP diagram showing what's going on as well, so we have an idea what's going on. So here's our saturation dome. So we start off with equality. So here's we start off with a certain, here is our isobar. We start off with a certain pressure P1, and this is our state 1 right here. 25% mixture. Now, what's the process look like? We're going from state 1 to state 2. Let's go back to the problem statement. So we have a rigid tank undergoing some sort of isochoric process where we're boiling away the liquid H2O. If it's rigid, what kind of process is it? It's isochoric. Rigid tank, that means isochoric. So I'm going to put up here in the assumptions, isochoric process. By the way, before we get too far into it, let me define my system here. So my system is going to be the H2O in the container. H2O in the container. Basically, what's happening with the electric heating element is we have an electric work interaction going on due to the heating element, okay? Okay, isochoric process until we get to a saturated vapor. So we're moving up here, and then that is state 2. Okay, and there's an isobar that goes through here. It's an isobar that goes through there. So there's P2 right there, okay? That's what the process looks like. That's what the process looks like. You know, that should be horizontal. That doesn't look good. That doesn't look good. Okay. There we go. Good enough. State 2, good enough. Okay, so that's the process. To calculate the time required to boil the liquid away, let's write the energy balance. Let's see what we get. But what version should we write up? We're interested in time. So maybe we should write the rate-based. Let's write the rate-based energy balance. Let's see here. Q dot minus W dot is equal to the time rate of change of total energy. Okay? That's the E balance for a closed system. Now, there's nothing in the problem statement about heat transfer. In fact, if I don't assume a heat transfer is 0, there's nothing about it. If I don't assume heat transfer is 0, I cannot calculate delta T because I don't know what Q dot is. I know what the work is, the electric work. It's a voltage times a current. So I think I need to assume away the heat transfer rate. So let's assume it is a insulated container and Q dot is equal to 0. I'm going to put insulated. Insulated container, okay? So I'm going to assume Q dot is equal to 0. What's the W dot term? Well, we know we have some electric work. No shafts, no propellers inside this tank. No shaft, no propellers, so there's no shaft work. It's a rigid container, so volume is constant. It's an isochoric process, so boundary work is 0. So electric work is equal to the work. I'm going to write here W dot is equal to W dot electric. It's an isochoric process. We're assuming it to be isochoric. No shafts in there, so I think that's a good assumption. W dot electric. Okay, that's what W dot is. Now, total energy, of course, is equal to DU. I'm sorry, total energy is U plus PE plus KE. So this DE dt is the change in internal energy plus the change in potential energy plus the change in kinetic energy of the system. Okay? And of course, you can go through and take these derivatives and you get du dt plus dpe dt plus dke dt. Now, the dpe and dke dt terms, they're due to a change in velocity or speed or a change in position of the system, i.e. gravitational potential energy. I don't see any indication that the rigid container is moving, accelerating in any way. So I'm going to assume away changes in potential energy and kinetic energy. So I'm going to write here PE is equal to KE and equal to a constant. Well, they're both, I'll tell you what, I don't write that. Let's not write that. PE and KE are equal to constants. Okay? That means they're not changing with time. 0. Okay, so all I'm left with is du dt. Let's write my final energy balance here. I got negative W dot electric is equal to du dt. Okay? Okay, we got a differential equation here, and I want to get a delta time T2 minus T1. I want a delta time or a change in time over the process. How do I get that out of this equation? Well, I'm going to multiply both sides of the equation by dt. Okay? So I got minus W dot electric dt, and then I'll have equal du. Okay, so I just multiply both sides of the equation by dt. Now let's integrate over the process. Integrate over the process. Let's see here. In the first integral involving W dot electric, the variable of integration is time. So over the process, we're going from T1 to T2. On this side, we're taking the variable of integration as internal energy. So from state 1 to state 2, we're going from U1 to U2. Okay? Now, the integral on the right is pretty easy. The integral of du from U2 to U1, or U1 to U2, that is U2 minus U1. Okay? That's the right-hand side integral, U2 minus U1, or delta U from 1 to 2, if you like. The left-hand side integral, well, the assumption here is the electric current's constant. So this is a current, and the voltage is constant. So the electric work is a current times a delta voltage. And this is a constant. So this voltage times current is constant. So W dot electric is constant. I can pull it out of the integral. And I get negative W dot electric integral dt from T1 to T2. What's that integral? Integral of time, d time from T1 to T2. That is delta T, or T2 minus T1, if you like. So this guy here, this is delta T from 1 to 2. Okay, let's write what we have. Let's write what we have. Negative W dot electric delta T from 1 to 2 is equal to U2 minus U1. Or if you like, delta U from 1 to 2. But I'm going to write U2 minus U1. All right. Okay, so we're interested in the delta T, the change in time, or the time required to boil away the fluid. That's equal to U2 minus U1 over negative W dot electric. Okay? If you're wondering what we're going to do about this negative sign here, remember the electric work or power is being done on the system. So this W dot electric will actually be negative voltage times current. Okay, so the negatives will cancel out and we will get a positive value for delta T. All right? Okay, so let's see what we got. Okay, I basically know what W dot electric is. That is negative current times voltage. I have both these things. Okay, so I have W dot electric. What about U1 and U2? What about U1 and U2? Well, U1 and U2 are mass times the specific internal energy at state 2, and mass times the specific internal energy at state 1. I know the mass. I don't know the specific internal energies at state 1 or state 2. In fact, let me rewrite that equation right here. I'm going to make my substitutions here. So let's write the equation one more time. Mass. Let me put the U1 and the U2 together. And then I have negative times a negative, or positive voltage times current times delta voltage. Okay? And again, I have delta voltage, I have current, I have the mass. I need to find U1, U2. All right? Okay, let's see how we're going to do that. Let's see how we can find the voltage. I'm sorry, the state U1 and U2. Okay. Let's see if we can find U1 and U2. Let's see if we can find U1 and U2. Let's see here, U1. That's equal to, we have an initial pressure, we have a quality. So U1 is equal to the specific internal energy of the saturated liquid, evaluated at 100 kPa, which is a bar, plus the quality at state 1 times, oops. I'm going to actually, hold on a second, I need to break. I'm going to break the lecture here. Okay, so let's calculate the specific internal energy at state 1. So that's going to be equal to U of the saturated liquid plus the quality at state 1 times U of the saturated vapor minus U of the saturated liquid. And of course, this is all evaluated at a pressure P1 of 1 bar. Okay, let's see here. Let's look some of these values up. Let's see here. Okay, so 1 bar, specific internal energy of the saturated liquid 417 and vapor 2506 kilojoule per kilogram. So I have 417 plus 0.25, that's the quality at state 1. And then U of the saturated vapor is 2506 minus 417, and that all has units of kilojoules per kilogram. Kilojoule, not kilogram. Kilojoule per kilogram. You crank that all out, and you see an initial specific internal energy at state 1 equal to 940 kilojoules per kilogram. 940 kilojoules per kilogram. Okay, so we've got 940 kilojoules per kilogram. Okay, so we've got the, we got the specific internal energy at state 1. Check. Now we need to get the specific internal energy at state 2. Now to do that, we have to know something about state 2. We don't really know anything in particular except that it's a saturated vapor. So state 2 is on the saturation dome to the left of the critical point. So we need to know another property to place us to know the state. We need to know something else about state 2 besides the quality. I need a temperature, I need a pressure, I need a specific volume. Specific volume. We know it's an isochoric process. That means that the specific volume at state 2 is equal to the specific volume at state 1. So specific volume at state 2 is equal to specific volume at state 1. It's a rigid container. Isochoric process, the mass isn't changing, so specific volume will stay the same. Let's see here, specific volume at state 1, let's calculate it. Okay, 1 bar, let's see, the saturated liquid is 1 times 10 to the minus 3. So 1 10 to the minus 3 cubic meters per kilogram plus 0.25. And then we have specific volume for the saturated vapor. 1.694 plus 1 times 10 to the minus 3. That's the saturated liquid. And this all has units of cubic meters per kilogram. I'm going to get a little lazy here. The 1 times 10 to the minus 3 is so small in both these terms. I'm going to neglect it, and I'm going to immediately calculate 0.25 times 1.694 cubic meters per kilogram. So 0.25 times 1.694, and I get 0.423 cubic meters per kilogram. Okay? So specific volume at state 1 is equal to specific volume at state 2, 0.423 cubic meters per kilogram. Okay? Now, oops. Sorry, I plugged in for all the specific volumes in my quality equation. There's the quality, 0.25. I neglected the specific volume for the saturated liquid, very small. And I just did 0.25 times 1.694, which is the specific volume of the saturated vapor. And I get 0.42 cubic meters per kilogram, okay? So we know this is a isochoric process. So here's V1 equals V2 equals 0.42 cubic meters per kilogram. So state two is a saturated vapor with a specific volume of 0.42 cubic meters per kilogram. 0.42 cubic meters per kilogram. Let's see if we can crank that out. So U2 is equal to U at a quantity of 1 and a specific volume of 0.423 cubic meters per kilogram. Okay? So how are we going to calculate this? How are we going to calculate the specific volume of a saturated vapor? So this is U sat vapor evaluated for a specific volume of 0.423 cubic meters per kilogram. That's what we're looking for. All right? Well, let's go back here. So let's see if we can find for a saturated vapor. Let's see if we can find for the saturated vapor a specific volume of about 0.42. Might have to do a little interpolation here. Vapor, 0.4, I see a 0.46, and I see a 0.37. So you're going to need to interpolate between these 2 points. Looks like it's going to be about approximately halfway between. Okay? So through a little interpolation, I find the specific volume at state 2 is equal to 2,557 kilojoules per kilogram. If you look here, 2,557 is approximately halfway between these 2 data points, okay? So, from interpolation, I get 2,557 kilojoules per kilogram. Interpolation. Okay, I interpolated between a couple of data points on the table. 2,557. Okay, so now we have U2. We've got everything. Let's plug in. Let's see here. We have 5 kilograms of the stuff. 5 kilograms. U2, 2,557. U1, 940. And this has units of kilojoules per kilogram. The current was 8 amps and the voltage was 110. So 8 amps times 110 volts. And amps times a volt gives you a joule per second. So notice the kilograms cancel out here. And this thing has units, so the voltage times, I guess I'll write it down one more and then I'll group all the units together. How about we do that? Got to be a little careful with this voltage times current. Let's see here. So we have 255.7 minus 940 times 5 divided by 8 divided by 110. And I get 9.18, and then my units are kilojoules, and then I have an amp times a volt. Okay, now the amp times a volt, as I said, had units of joule per second, or if you like, a watt. A joule per second. I need to convert that into kilojoules so that it will cancel out properly with what's in the numerator. Let's see here. So there are 1,000 joules per kilojoule. Okay, the kilojoules cancel out and I get joules. The joules cancel out and I get 1 over seconds. So I get 9.18 10 to the 3. Joules cancel and I get 1 over seconds and I get seconds. So delta T is equal to 9.18 times 10 to the 3 seconds. If we want to rewrite that in terms of minutes, so there is 60 seconds per minute. The seconds cancel out. So 9.18 times 10 to the 3 divided by 60, and that gives me 153 minutes. 153 minutes. Kind of going off the board here. So the heating time is equal to 153 minutes. That's it. Heating time is 153 minutes. Okay, so this is kind of an interesting problem in the sense that we had a two-phase mixture to deal with, not an ideal gas. So that complicated things a little bit. We had a quality to worry about and using the saturation tables. We also had time in this problem. So I used the rate-based energy equation and then integrated it over the process to extract out a delta T, which is what I'm looking for. And by the way, I think I was calling this delta T from 1 to 2. Delta T from 1 to 2. Okay? All right. Okay, let's move on to some new material here. Remember I said we were going to be revisiting specific heats? That's indeed what we're going to do. Specific heat revisited. Or if you like, the du, dh property relationships. What do I mean by property relationships? I mean how one property changes with another. Okay, you'll see what I mean in just a minute. Okay, let's say we have a system. Let's say we have a system, and the system is undergoing an infinitesimal or differential process. For example, it starts off at the initial state with some specific internal energy U, and in the second state, it ends up with a specific internal energy U plus a change in U. So U plus du. So an infinitesimal or differential process. The system is moving over a small change in property. Temperature starts off at temperature T and ends up at temperature T plus dt, for example. Okay? So we got a differential process going on here. Let us write the energy balance for this system. It's a differential process, so let's write the differential energy balance. Del Q minus del W is equal to the change in energy, differential change, which is equal to the differential change in internal energy, plus the differential change in kinetic energy, plus the differential change in potential energy. Okay? By the way, before we get going here, this could be specific internal energy or it could be internal energy. Why don't we make things a little clearer here? Let's make this internal energy instead of specific. It doesn't really matter. But let's be consistent with the energy balance that we wrote there. Okay, so this has an internal energy U, and it changes by an amount du over the infinitesimal process. Temperature changes by an amount dt. Okay, so let's apply this equation to the system. Now, let's say, how do we go from one state to another? So let's say this is state 1, and this is state 2. Okay, this is a differential process. This path is really small. I'm exaggerating it. Okay, so we're going from state 1 to state 2. It's a differential process. That's why I have du's and dt's in there. Okay. Now, I'm going to put some restrictions on this process. I'm going to load this process up with some restrictions. It's not only a differential process, I'm going to make it isochoric. So, restrictions. Restrictions. Number 1, isochoric process. Okay? Now, what does that imply? That implies that the little bit of heat transfer, del Q is equal to m CV dt, and that's the definition of specific heat. Remember, specific heat was defined as, let's see, CV was the little bit of heat transfer divided by the mass of the system times the differential change in temperature for a constant volume process. That's the definition of CV. So I'm using that to point out that del Q, the heat added, differential heat added, is mCV dt. So this guy here is mCV dt, if it's an isochoric process. By the way, if it's isochoric, what's the boundary work? It's 0, no boundary work. In fact, I don't see any wires or shafts in this system. So I'm just going to say all work or differential work is equal to 0. No shafts, no wires, isochoric, no boundary work. So there's no work going on. So this term is equal to 0. Okay? Let me load up a couple more assumptions. Let's say that the system is not moving, it's not accelerating, it's not changing position, it's just sitting there. So I'm going to say dPe dKe, the change in internal and potential energy, those are both equal to 0. Okay? The system isn't moving, it isn't accelerating, so I'm going to get rid of these terms. All right. The key here is isochoric process. That's the key. Okay, that's the key. All right, let's write what we have left. Let's write what we have left. Del Q, so we have m CV dt is equal to du. There's nothing left. There's nothing left. mCV dt, that's the heat transfer, and I have du, nothing else left. Now let me divide this equation by mass. Well, the mass cancels out here, and then this becomes specific internal energy. Okay? Now remember here, this was for a constant volume process. So I do want to say here, volume equals constant, isochoric process. Let me flip the equation and write down what I have. du for a constant volume process is equal to CV dt. Okay? You give me the change in temperature and the specific heat, CV, and I'll give you the change in internal energy. This is for a differential process. Now, Here's the clincher. Internal energy and temperature, specific internal energy and temperature, are both properties of the system. If this were internal energy here, specific internal energy, and this were temperature, it doesn't matter what path I take to go from state 1 to state 2. I could do any path I wanted. So it didn't matter that I took a constant volume process. I could have taken any process, any path between these two endpoints over this differential process, and I would get the same equation. U and temperature are properties, so their changes are not path dependent. They are point functions. So, note, U and T are properties, in other words, point functions. So their change, dt and du, are invariant with respect to path. I can get rid of this. V is constant. I don't need it anymore. So this implies du is equal to cv dt for any process. Box it up. That's our first property relationship. You give me the change in temperature, you give me the specific heat at constant volume, and I can calculate the change in internal energy. Now that's a differential equation. So if I want to get delta U from state 1 to state 2, this is for an overall process, all I got to do is integrate this. And so it's the integral of CV dt from T1 to T2. Okay? If I want it for an overall process. Okay, so let me just say a few more things about this. Let me write this one more time. du is equal to CV dt. Okay, so let's put a box around it. Now, one last little thing before we move on from that differential equation. It's not valid in the dome. Why? Because property changes can occur when temperature is constant. When you're inside the dome, so here's your temperature and specific volume, here's your isobar. You can move from one state to another, yet keep temperature constant. So that equation, that property relationship, is not valid inside the dome. It's valid for gases and for solids. No phase change. So I will write here, note, not valid through a phase change. What does that mean inside the dome? Not valid inside the dome. If you're a superheated vapor, or you're a liquid, or you're a solid and incompressible, you're not changing phase, you're fine, but not valid inside the dome. Okay? Again, the overall process version of this, if I integrate this equation for a finite, an overall process, delta U1 to 2 is equal to the integral of CV dt from T1 to T2. Okay? So if you want to find delta U, you just have to integrate the property relationship. Now, in general, CV is a function of temperature. It's a function of temperature. Remember, we have these ideal gas tables. Let's see, we had ideal. Let's go to ideal gas. Let's assume we're working with an ideal gas. Let's go find specific heat as a function of temperature. Okay, specific heat, CV, CP are functions of temperature. Okay, so to integrate that equation, you need to know what CP is as a function of temperature. Remember, I think I mentioned this before. If you want to evaluate that integral, you can use this polynomial. It's a fourth order polynomial giving specific heat divided by the gas constant as a function of temperature. And the constants alpha through epsilon are listed here for various substances. Here's air right here. There's air. Okay? So if you want to evaluate that integral exactly, if you want to evaluate this integral exactly, you'll have to find out the relationship of CV as a function of temperature so you can determine what delta U is via the integral. Now, sometimes temperature changes are small. So if delta T is small, or delta T 1 to 2 is small, then we can assume specific heat is constant. CV, which is a function of T, is approximately equal to a constant. And so delta U from 1 to 2 is approximately equal to CV, and it'll be some average value of specific heat, like evaluated at the average temperature. T2 plus T1 over 2 times delta T from 1 to 2, okay? So this integral, if we assume constant specific heat, delta T is quite small. We can pull the CV out of the integral, and I get CV integral dt, and that gives me CV delta T from 1 to 2, okay? If delta T is small. All right? So this is our first property relationship. du is equal to CV dt. Specific heat is typically a function of temperature. So evaluating, integrating this can be a little bit tricky sometimes. Usually we just assume constant specific heat when we do most problems. If you want more accuracy, you can either use property tables or you can get a polynomial expression for CV and then integrate. Now there's one more property relationship. I'm not going to go through the derivation here, but I will make it plausible. If instead we do a isobaric, so now let's say we do isobaric. If we do an isobaric process, then the work is equal to the boundary work, which is equal to PdV. Okay? And what I get instead is another property relationship for enthalpy. If I just change the path of integration and make it an isobaric process, I get a dH property relationship. By the way, if it's an isobaric process, then del Q is mCp dt. mCp dt for a constant pressure process. Okay? Do the same exact derivation. I will have a boundary work term. It'll have a PdV in there. And I'll end up with the dH property relationship. The differential change in enthalpy is equal to the specific heat at constant pressure times the differential change in temperature. Box that up. The same restrictions apply to this equation as they do for the du equation. not valid inside dome, but valid outside the dome. Valid outside the dome. Superheated vapor in particular. And then, of course, delta H from state 1 to state 2 is equal to the integral of Cp dt from T1 to T2. And if you want to assume constant specific heat, you can pull this out of the integral and you get Cp evaluated at some average temperature times delta T. So sometimes for a small delta T, delta H is equal to approximately Cp evaluated at some average temperature times delta T 1 to 2, okay? Delta T 1 to 2. Now I want to say one or two more things about this. There's two more details I want to go over. So for the isobaric process, where we derive that equation, we have boundary work. If it's a constant pressure process, the system can be expanding or contracting, and it's an isobaric process when we have boundary work. Now, if you have a solid or a liquid, liquids and solids do not compress very easily. Their change in volume is quite small. So for a solid or a liquid, there's no boundary work, and these results must be the same. In other words, for a solid or a liquid, Cp is equal to Cv. Put a little box around that, all right? They must be the same. Cb is equal to Cp. The reason there's difference between these two, dH and du, is because of boundary work. If it's a solid or a liquid, there's no boundary work, okay? Now, one last little thing I want to say, and this applies to ideal gases. Remember at one point I stated the following. Recall. There's a relationship between Cp and Cv for an ideal gas. Specific heat at constant pressure is equal to specific heat at constant volume plus the gas constant, R. I mentioned this last time. Let's see how we derive this. Let's see how we derive this. Let's see here. Proof. dH. Remember enthalpy. H is equal to U plus pressure times specific volume. Specific enthalpy is specific internal energy plus pressure times specific volume. So dH is equal to du plus PV. Okay? Now, let me apply the differential, and I get du plus d pressure times specific volume. Now, dH is equal to Cp dt. du is equal to Cv dt. Okay? So let me write what I've got. Let's write what I've got. Let me move over to the next board. So I got Cp dt, which is dH. Cp dt is equal to Cv dt, which is du. And then I have a d pressure times specific volume. Now, What if we assume ideal gas behavior? What's pressure times specific volume? Let's write down the ideal gas equation. IGB, pressure times volume, is equal to mass times the gas constant times temperature. Okay? Let me divide both sides of the equation by m. These cancel out, and volume divided by mass is specific volume. So this is actually equal to pressure times specific volume is equal to RT. Let me substitute pressure times specific volume into here. So that is RT. And so I get CV dt plus DRT. Now, R is the gas constant. It is a constant. So it comes out of the derivative or the differential. So this is equal to CV dt plus R dt. Let's write down what I got. Cp times the differential change in temperature is equal to Cv times the differential change in temperature plus R times the differential change in temperature. Let's cancel out the differential change in temperature. What do I have left? Cp is equal to Cv plus R. So for IGB, the relationship between Cp and Cv is Cp is equal to Cv plus R. Put a box around it. This is valid for IGB. Ideal gas behavior, okay? So if somebody gives you a gas and they only give you the specific volume at specific heated constant volume, and you've got to find the specific heated constant pressure, boom, there you go. You can use that equation. All right, ladies and gentlemen, I think we've done a lot today. We've done one example and a bunch of theory. I think you're tired. It's the end of the week, or it's the end of the week for me, the beginning of the week for you. And I will say goodnight.